All right, this is a video over Algebra 2, Unit 1, notes on relationships between quantities, okay? And the first section we're going to talk about is the real numbers, okay? And so our objectives today is we're going to classify real numbers, okay? We're going to describe what they are. We're going to identify the field properties of real numbers, and then we're going to represent real numbers with variables. So let's go ahead and talk about the different types of numbers that we have. Okay, so the first one we have the natural numbers, okay, and what I like to call these counting numbers, okay, and so this set of numbers, this group of numbers, all right, if I said natural numbers, that would be the numbers 1, 2, 3, 4, and so on, okay, those are those kinds of numbers. All right. If I were to talk about the whole numbers, that would be the counting numbers, not numbers, numbers. Okay, these would be the counting numbers and 0. Okay, and 0. So this would be the set of numbers 0, 1, 2, 3, 4, and so on. Okay? All right. Integers would be the whole numbers and their opposites. Okay, so we would start with, like, say, -3 and go -2, -1, 0, 1, 2, 3, 4, and so on. Okay? So the thing I want you guys to see about this is that hopefully you notice that when you say the word integer, that includes the whole numbers and it also includes the natural numbers, okay? All right, let's talk about what a rational number is. This is a ratio, okay, a ratio, okay, / fraction, whose decimal stops or repeats. Okay, so there's quite a few numbers in the rational number system. So an example of this would be something to the effect of, say, like 3/2 would be a rational number. Okay, 3/2 as a decimal is 1.5. Okay, this stops. Okay. If you had, say, 2/3, that's 0.6 repeating, right? That keeps going on and on and on and on. Okay, that's a repeating decimal. Okay, all right. What about the number like 3? Is that a rational number? Okay. If I were to write 3 as a fraction, I would say that this is 3 being divided by 1, which is equal to 3.0. This decimal stops. Okay? If the decimal stops, then it's a rational number. Or if the decimal repeats, it's a rational number. Then go ahead.
So with the 5, it stops why?
The 5, because there's no numbers after it. Pi, so
that's irrational.
That's irrational. That's not a rational number.
But also so whatever repeats itself.
Right.
Okay.
Okay, if it repeats, like let's say, like if you have, I think it's 2/9, isn't that's 0.2 repeating. 0.22222. That the 2 keeps repeating. Okay. Let's say you had the decimal like 0.1 171717. That repeats. It has a pattern to it. If a number doesn't have a pattern, if you like find a number and all of a sudden it just keeps going and going and going and there's no pattern to it, that's irrational. Okay, great question. Great question. Okay, so irrational, that means that the decimal doesn't repeat and doesn't end. Okay, so the decimal doesn't repeat and doesn't end. Okay, so an example of this would be like pi. Okay, pi is a number. Pi is approximately 3.1415926, and it just keeps going. And it doesn't ever end. It doesn't repeat. It doesn't have like a sequence to it. It just keeps going. Okay, so another irrational number would be the number the square root of 2. That's like 1.41, and it keeps going. Okay? And so what we do for those irrational numbers, we use the value pi, we use the value square root of 2. We don't really use the decimal approximations of those. Okay? So then we have the real numbers. Anybody know what the real numbers are?
It's the entirety of all of them.
Any number. Any number on a number line. Okay, so that's the thing, is that all real numbers, okay, every one of these types of numbers are under the real number system. Okay? Irrational numbers are different than rational numbers. Okay? All these are a little bit different, but they're all under the category of real numbers. Okay? All right, so let's take a look. If we had something like this. All right, so let's just take a look at this first problem here. It says choose all sets that contain the number negative 2.22. Okay? So because it's a number itself, okay, I know it's a real number. Okay? You can always say that. Okay? It's always a real number. Is it and the only, the thing that I notice is we have decimals. So it can't be an integer, it can't be a whole number or a natural number. Those are like counting numbers, and they're opposites, okay? But does the decimal stop?
Yes.
Yeah, negative 2.22 stops. There are no numbers beyond that. So because that stops, we know that it's a rational number, okay? So those are the only two sets that it falls under. It's a rational number, so therefore we know it's a real number. Okay, let's take a look at the number 5. Ooh.
It's everything but irrational.
Right, it's everything but irrational. We know it's a real number, it's a number, okay? It's a natural number, it's a counting number, okay? If it's a natural number, then we know it's also a whole number. If it's a whole number, we know it's also an integer.
Wasn't it the other way around though?
Kind of.
A natural number, it can't be a whole number.
Mm-hmm.
Because
Yep.
0 is not a
Well, 0 isn't a natural number, but we're not talking about 0.
Yeah, I'm just saying like
Yeah, but we're just talking about 5. So it's all of these. The decimal stops. Okay, if you had the number 5, if you take 5 divided by 1, you get 5.0. That number stops. It's a rational number. Okay? Okay. Let's take a look at this question here. It says, select all the following statements that are true. All real numbers are natural numbers. No. All whole numbers are integers. This is true. Okay. All integers are whole numbers. That's false. All natural numbers are rational numbers. That's true. Okay. And this is false. Okay. The way that I can tell is that, natural numbers are the counting numbers. Okay, whole numbers are counting numbers in 0. Each of these groups of numbers, except for irrational, are a part of the one below it. Okay, so it goes this way, doesn't go this way. Okay, so it says a real number plus a real number is another real number. So we say that the set of real numbers is closed under addition. Okay, it says, it asks us the question, which other sets are closed under addition? Okay, and when it says closed, that means that when you add two of the same numbers, add two of a type of number, you get that type of number, okay? You get that, get that type. All right, so how I would say this, okay, it says which other sets are closed under addition, okay? I know the natural numbers are closed under addition. Okay, the natural numbers. I know that the whole numbers. And I know that, what's it called? Natural, whole, what else? Integer. What else? Rational numbers? We know real numbers are. Natural, whole, integer. Okay, let's just say that for now. Okay, and the reason is this, okay? If I were to take like a natural number like, say, 3, all right, and add another natural number to it like 4, I get 7, okay? 3 was a natural number, 4 is a natural number. If I add those two together, I get a natural number as a result.
What if, like, I mean, what if,
Like let's say you do like 0 plus 3. These are both whole numbers, so then as a result you get 3, which is a whole number.
yeah, which also means it's a whole number.
Yeah, and you can say the same thing about integers. You know, if you take like -2 plus -7, that's going to give you -9. Each of these are integers, and as a result, you get integers. That's what closed under addition means, okay? And I actually think that they're all. I'll have to look this up. I can't remember which.
I don't know about rational.
Well,
That's kind of confusing.
it's kind of confusing. Let me come back to that, and we'll kind of dive into that at a later date. Okay, and it says which numbers are closed under which operations. Okay.
Whole numbers. I think
Oh, whole numbers are closed under which operation. So if I take a whole number, well, for sure we can do addition. Okay, we know it's closed under addition. Is it closed under subtraction?
I think so. Well, whole numbers. Oh, no, because if you do like the, well, yeah, should be.
Well, but if I do, okay,
Can't be negatives.
right, they can't be negative. But if I
But you
take
can get a negative.
if I take 7 minus 9,
Yeah, you get a negative.
I get -2. That's not a whole number. So no, not under subtraction. What about multiplication? What about under times?
Should be, yeah.
Should be, yeah. Because if you take any number, any counting number and or 0, you'll multiply them together, you get another counting number or 0.
Yeah.
So that works. So addition, multiplication. What about division?
Sorry.
Better be sorry. What about division? If you take 3 divided by 2, dividing two numbers that are whole
I
numbers,
think you might be able to get an irrational.
you get a rational number here. You get 1.5.
Can't you get an irrational?
So whenever you do 3 divided by 2, it's a rational number?
This would be a rational number. So if I were to take these two whole numbers and divide them, am I getting another whole number? No.
But can you if you divide?
Oh, sure. I mean, like if you did 4 divided by 2, you'd get 2, which would give you another whole number.
Oh, yeah.
But it has to work for all of the numbers,
Okay.
not just some of them. Okay? So if you can disprove it, then it doesn't work. Okay? So no. False. Okay. All right, so which set is closed under subtraction?
Whole numbers? No, wait, no.
That's closed under subtraction. Rational are definitely, right?
I would say rational.
It's only one, right? Only one.
Well,
That makes sense, though, right?
it would either be rational or irrational. It'd be one of those two. It wouldn't be these. Okay. All right, then it says this. Which answer choice shows the set of irrational numbers, is not closed under addition?
Well, I remember this one. I think it was the first one.
Okay. Which answer choice shows that a set of irrational numbers is not closed under addition? Okay, so check this out. Look what you get. These two numbers are irrational. Okay, if you add them together, do you get an irrational number?
I mean, it depends.
Yeah.
Depends on what kind of irrational.
Well, irrational number means that the decimal doesn't repeat or end.
Actually, yes,
Zero.
You wouldn't know, so you can't.
Right.
There's no
Yeah.
possibility.
It's this one. Okay. Next page. All right, let's take a look at this next page. Okay, it says the following examples illustrate the commutative property of addition. Okay, and what you notice here, these examples, all you're doing is you're rearranging the order in which you add numbers. Okay, so commutative property means reorder. Okay, and this is a really powerful property. Okay, and here's how we know that. What's 3 plus 2? It's 5. Well, what's 2 plus 3? Still 5. Okay, if you're adding two numbers, you can reorder them. All right? And so then it says, okay, all right, study the examples, then choose the one that best describes the property. Well, which one shows that if I look at the left side of the equal sign or the right side of the equal sign, which one shows that they've reordered the numbers? It's this last one. Okay? Because all they've done here is they've just reordered these numbers. Okay? Now, the same thing works for multiplication. Okay? You can reorder them. All right? Okay, let's ask. What's 3 times 2? What's that equal to? 6. What's 2 times 3? That's still 6. You're going to get the same thing. Those statements are equivalent. Okay? So on this one, it says which of these shows the property of commutative property of multiplication, and it's this one where you just reorder things. Okay? And you can have a number of them that you reorder, but it doesn't matter. Okay? And I'll use this quite a bit. Okay? All right, the associative property, okay, this shows the associative property. I think this got screwed up, and I don't think it's on your paper. Associative property means you can regroup.
Yeah, that's on.
It's on your paper, it's not on here.
Mine.
Okay, you can regroup, all right, and you can regroup for multiplication. Now, watch what I do here, all right. Let's say I were to take the quantity 3 plus 2 and then add 4 to that. Okay? If I take this, then that's going to give me 3 plus 2, this is 5, plus 4, this gives me 9, right? Okay? Now what if I do this? What if I take 3 plus the quantity, 2 plus 4? Notice how my groupings have changed. I still have the numbers 3, 2, 4 and 3, 2, 4. It's just that I've grouped them in different ways. Right, so then I'm going to get 3 plus 2 plus 4, which is 6. What's 3 plus 6? 9, you get the same thing. Okay, that's the associative property. Okay, same thing with multiplication. All right. If I take the quantity 3 times 2 and then multiply it by 4, okay, that will equal the same thing as if I take 3 times the quantity 2 times 4. All right, so 3 times 2, that's going to give me 6 times 4, and that's going to give me, what is that, 24? Okay, here I'm going to get 3 times the quantity, 2 times 4 is 8. 3 times 8 is also 24. So you can regroup things, okay? This is important because there will be a time when I will reorder things for it to make sense, okay? I will actually do these properties quite a bit, all right? So it's important that you know them. You've probably learned them before, but we just got to go over them anyway, okay? All right, the identity property of addition, okay? Identity means you keep the same, okay? So keep the same, all right? So if I had the number 3, what would I have to add to that to give me 3? Yeah, add 0. Okay, that's what the identity property is. If I take any number and add 0 to it, I still get that same number. Okay, same thing with multiplication. 3 times what number is going to give me 3? 1. That's it. Keep the same. I have my identity. I wear flannel every day. If I don't add any more new flannel, do I change my appearance? No. If I add 0 things to my wardrobe, I'm going to keep wearing everything, all the same stuff for the next however many years I'm alive.
Change the brand.
Eh,
People change and they respect it more.
that's fair. All right.
Maybe fashion changes.
Okay, so this inverse property, okay, when we do inverse property of addition, that means bring back to 0. Okay, that's what that means. Inverse property is bring back to 0. So it really means that you take a number and add its opposite. All right? So it says on this one, if you take for real numbers, a plus negative a will give you 0. All right? 5 plus negative 5 gives you 0. Negative 1.33 plus 1.33 gives you 0. All right? A number and its opposite. Okay? All right? Inverse property of multiplication. When you talk about multiplication, that means bring back to 1. All right? And the way you do that is you multiply by its reciprocal. Okay? Reciprocal means you flip the fraction. Okay? And so here's what you've got. The property that they have is, using this math jargon, a times 1 over a is going to equal 1. But let's kind of talk about this for a second. And I love fractions, by the way. They're like the best thing going. If I take 5, what's 5 as a fraction? What am I dividing by 5 right now? 5 over 1, right? Now check this out. If I wanted to multiply this by some number to get 1, okay, then I would have to multiply this by 1 over 5. Now here's the thing. When I add fractions are our friend, okay, I'm going to multiply 5 times 1. I'm just going to multiply across. So when I multiply these two fractions together, I take 5 times 1, which gives me 5. 1 times 5 gives me 5. What's 5 divided by 5? It's 1. That's all you're doing. Okay? But just a formality. Ooh, the distributive property. This one's fun. Okay. When you have a number on the outside of the parentheses, when you are some number times the sum of two other numbers, then you have to take a times b and a times c. Everyone remembers this one, right? Yeah, distribution. Okay, so yeah, like if I were to distribute papers, I'm the one on the outside, I'm the A, and I'm passing papers to everyone on the inside, and that's what you do. Yes. Well, FOIL is an acronym to use the distributive property twice, but yeah, you're right. Okay. So someone asked me this over the weekend. They said, hey, Joe. They were like, hey, what's 17 times 6? And I'll tell you, my mental math sucks. Okay? Yeah, you can use a calculator, or you can rewrite this and say, all right, well, what's 10 plus, how could I rewrite 17?
It's 102.
How could I rewrite 17 as the sum of two numbers? What could I do?
10 times 6,
I mean,
7 times 6.
Yeah, that's what I do.
Yeah, so if you split this up and you go, okay, well, what if I take 10 plus 7 and then multiply that by 6? Because if I took 10 plus 7, then that's going to give me 17. And I could easily distribute these numbers, okay? And I could take 6 times 10 in my head, which I know is 60, plus 6 times 7. And so then you get this. Then you get 60 plus 42, which is 102. No, we did it wrong. We said it was 112. Whoops.
You said it was 112.
It wasn't me. It was somebody else. Oh, wait a minute. Yeah. We're good. It's 102. We're good. Everything's cool. Everything's fine. Okay, on this table, these are just different ways to say things. You know, if these are all the operations that we have. These are words that represent those operations. Okay, I would refer back to this. But if you say 3 less than a number, okay, less than means minus. Okay, a number, x, and there is 3 less than that. Something like that. Okay, the quotient of 2 times a number and 4 is 6. Oh, dear Lord. Okay, hold on. The quotient of 2 times a number and 4, 2 times a number, wait a minute. Yeah, I know, isn't this terrible? The quotient of 2 times a number and 4 is 6. Wait.
4 is 4. You can't just change numbers.
Well, it says is 6. Is another word for equals.
Oh.
Yeah. So I got something that's going to equal 6. Okay? Quotient means divide. The quotient of 2 times a number and 4. 2 times a number. The quotient of 2 times a number and 4 is equal to 6. Kind of hard.
Wow.
Well, just
I think that's it. I could totally be wrong. Anybody fill out the notes? And I think that's it. You got to have some sort of division in there.
So like the end product of some number that was divided times 2 equals 6.
x equals 3.
I mean, it's 2 times, it has to be 2 times x.
Yeah,
And it
if you
says
multiply.
and 4, so that's addition, and then is 6, so, and then the quotient is just there, so it's probably like that.
Yeah, you got to have some sort of division in
It's
there.
thrown in there.
Of 2 times a number, which is here, and 4. So the quotient of 2 times a number and 4.
That's like the overall
God, I don't like
of the.
Yeah, it's rough, man. Okay. All right. My friend Tyrone bought a calculator and 2 packs of batteries for $42. Depends on the calculator. So Tyrone bought a calculator and 2 packs of batteries for $42. So let's say X is the calculator, price of the calculator, plus 2 times Y. Y is the cost of batteries, and that's equal to $42. Now the crazy thing there is I created variables. Ugh!
Wait, what's x?
X is equal to the cost of the calculator. Okay.
That's the calculator.
Mm-hmm. Calculator. Y is equal to the cost of batteries.
There you go.
Never assume. Okay? And that's the thing. And that's the crazy thing about this is that I created this. This was created.
Is there even like a way to solve that though? I don't think there is.
Kind of depends. You could solve it for one of the variables. All right, let's finish this. Okay, on this last one, we've got It says choose the expression that represents 3 less than 7 times a number. So let's just write that. 3 less than 7 times a number. So I'm going to do 7x minus 3. Okay? 3 less. When you see that, that's always subtracting a 3. Okay? And that usually goes on the right side. You could also write this. You could say negative 3 plus 7x. That would work too. Okay? That works.
I started to actually write it that way, then I went to continue.
That's okay. But subtracting a number is the same thing as adding its opposite. Okay? All right, then the one says choose the expression that represents the product of a number. Oh, God. And 5 is 2 less than the, oh, for God's sakes.
Give a number so that's an addition, right? Product, or does that just mean?
All right, hold on. The product of a number and 5, so 5x, is, that's equals, 2 less than a number. So I'm going to do x minus 2. Boom. These are tricky.
5x what?
5x is equal to x minus 2.
How does that work?
Well, okay, so look. It said the product of a number and 5.
Oh,
So 5x is
yeah.
is equal to.
I thought product meant equal as well.
Product means multiply.
5 is
Multiply?
2 less than
Mhm.
the number, that means the number is 7.
I don't know.
If 5 is 2 less than the number, then the number is 7.
No, because if you plug that, you could solve that algebra. It's a fraction.
Well, wouldn't it be 5x minus 2 instead of 5? Oh, no, because that
Is.
Okay. Because
Yeah, it's tricky.
it kind of is because on the first one it says that 3 less than 7 times the number, and then this one says is 2 less than.
Is 2 less.
It's just confusing how.
It is confusing.
Because I wouldn't, if you were me doing this in a group, I would not put the x, I would just put the, probably equals, I don't know.
That's all right. That's what we practice. Okay. Okay. Write the expression using words. So negative 5x times the quantity 4 plus 3x.
We have to write that out?
Yeah. All right, hold on. Let me finish this. All right. Sum of a negative 5 times the number. Okay, hold on.
You got this.
Oh, so you have to wait. So then, what's that?
Okay, it's okay. So you have to read it. You have to say, okay, the product of 3 times a number.
Oh, which one of these is that?
Yeah.
Oh,
Okay, hold on. The product of negative 5 times the number and the quantity 4 plus 3 times the number. That's the one. Okay. So the product of negative 5 times a number, that's this part right here. Negative 5 times some number x. And the quantity 4 plus 3 times that number x.
So the quantity would be, that's how you know to put it in.
That's how I know, because you put it in parentheses. Okay? A lot of this stuff is pretty tricky, guys, but we'll get better at it, and we'll have fun. Trust me. All right, talk to you later. Bye.